Hi guys, welcome to another Learning Electronics Repair video. I've been brought this PCB in today. Somebody called me yesterday and asked if I could fix this. So this is from an air hockey machine. These are the things you see in arcades, amusement arcades. I'm sure wherever in the world you will see these things. So it has like a big flat table with little holes in it which blow air, and you have a puck which floats around on, and you hit them with these other pucks and you score goals basically, yeah. So this is an air hockey machine. This is the PCB out of it. Now what's happened with it is this fuse blew, this 7-amp fuse. So the fuse went. They've replaced the fuse and it now powers on, but like the LED displays, the numerical displays for the scores come on dimly and nothing else happens. Yeah, that's what it's doing or what it's not doing. And then they said, well, Rich, can you fix it? And I said, yeah, I'll have a go at that. Why not? Yeah, why not? I mean, at the end of the day, it's all just electronics really, yeah? So it's all electronics at the end of the day. What can we do with it? Well, the first thing I noticed is there's one fuse here and there's two other fuses missing, but they said that only the middle fuse is required. You don't need the other fuses. So that's the first thing I've been told about it. Having a look around it, there's a couple of devices here with heat sinks. There's another fairly, well, there's a TO220 power device here. And if you look underneath, this is like burnt or dark where that one is, okay? What are the devices? Well, let's have a look, shall we? Let's zoom down. Well, straight away it says IC22, so it's not a transistor, it's probably a voltage regulator. Oh yeah, 7805, 1 amp or thereabouts, positive voltage regulator, so that's that. Also, this capacitor is bulged, yeah, can you see at the top of that? There's a bit bulged, so that's gone. That might be connected to this actually, it looks like it's in that area of the circuit at least. You normally expect to have a capacitor on the input and the output for a regulator, but I'd be surprised, yeah, maybe that would stop it from working. We have some diodes here, a whole load of them. Yeah, another one here. Bigger capacitor. Here's another IC, probably another voltage regulator. What have we got? 7812, 12 volts positive voltage regulator. Okay, that's that one. And there's another one. This looks like another voltage regulator. Another 7805 positive voltage regulator. So we've got two 5-volt regulators. We've got a 12-volt regulator. We've got a Duff capacitor. Yeah. What else can we see? And this is where it looks like it's a bit burnt underneath. So that's got to be worth a look. These fuses, but you say only the middle ones need it. Well, one end of all the fuses, they're all connected together, and then these are all separate. Oh, I see. Can you see the tracks? This is the transformer. Oh, these will be different taps on the transformer. Yeah. 120, 220, 240. So yeah, we're on 220 volts here. So that's what they are. So effectively you put whichever fuse you want, which not only acts as a fuse but also selects the voltage you want. So that's on 220 volts. That's why I need one. The power then. So this is line. This says load, yeah. So this is like a mains filter. It's like a filter on the mains. So load is this end. And this is what goes, well actually, that goes to like the transformer, yeah, there. That's this end of it. And line, which is the other end of it, this goes to the end of the fuses. So, yeah, it must come through the fuse, through the filter, and then into the transformer. This looks like it's a ground terminal, you see that there? Yeah, high voltage capacitor, so that's a ground. Let's just zoom out a little bit. Okay, we can see it a little bit broader now. There's an earth symbol here as well. I bet this is where the power comes in. I wouldn't be surprised if it's by this, yeah. Let's have a look. So, well, that goes to the earth, and we know it's earth. Oh yeah, can you see? So this pin goes to one of the inputs on this filter. Ah, this doesn't go this way to this way. I can see it now. So this, it says a line which is in front of these fuses. That's not those, that's the end of the fuses, yeah, that's here, these two. These are the inputs to the filter. One end comes from here and the other end comes from here. So that's your live and neutral in. Yeah, we know where the power comes in now, those two. And then the other side of this filter, one goes to this end of the transformer and the other one goes down to the fuses, which selects whichever one and comes back to the transformer. Right, so we know now where the power comes in. Another good indicator that is the case is that there's a big gap down here and along here to here, and it's normal to separate the high voltage side from the low voltage side of a circuit board. What else can we work out with this? Well, let's have a look through the board. So you can see here we have a load of diodes. It looks like two ends of these connected together, two ends of these. It's probably a plus and minus supply coming off here. I'm not sure. Well, they could just be wired in parallel. Hard to say. I need to track it out. But there's another two there. They connect together. Yeah, and this one looks like it goes that goes to this capacitor, and probably goes to this voltage regulator. Yeah, so that's that. This one comes from here, and it looks like it goes to down here. Not sure if it goes to this voltage regulator. That seems to go to this capacitor. That's the one that's gone. What else do we have? We have some more diodes just getting into shot for you guys. Some more diodes down there by the side of the transformer. There's two more capacitors. And this is where the 7 amp fuse comes from. So this is the fuse that had blown, okay? And that goes off under here. Might go to this one. I haven't checked out yet. Where does that seem to go? I have to track that through, can't easily see. But the 7 amp fuse goes off down that way somewhere, yeah? This was blown, so we need to find out where that goes. That gives some idea why did the fuse blow, but it doesn't blow now. Yeah. We also have, if we look down here, some sort of modification that somebody's made. I don't know if this is a repair or some sort of modification, but if you look at it, you got these two chips, yeah, and the tracks have been cut here and here, so that comes to this pin and this pin on this chip. They've been disconnected, and these points have been connected to the other chip, yeah, here and here. So whatever these chips are, they're probably driving something, and this has been set so whatever's being driven are both coming from that, if it's just two separate things. So if we look to see what these chips are, that might help us figure some of that out, okay? This is ground. I know this is ground. Reason being, it goes to the middle pin on the two 7805 and 7812 regulators. And I know, without looking at the data sheet, the middle pin is ground. So that comes from the transformer, and it obviously goes off over here, so ground goes into this somewhere. I'm guessing this is probably all ground as well. We have then 3 lots of switches, and these are pull-up resistors. I'm sure these will be pull-up resistors. They could be pulled down, so the common end is ground, but more likely they pull up, so the common end is 5 volts or something like that. And these obviously set some parameters for the game, the machine. We got one here, and this one's connected into this chip. I suspect this is the processor. But there's not lots and lots of pins going. These are all going to the pull-ups. And I'm guessing the switches pull the various signals down when you switch them on. Are they related to this somewhere? These might be shift registers, I'm not sure, because there's lots and lots of switches and only a few pins on here. So you'd expect this to be serial information from these parallel in, serial out, some sort of shift register, maybe. Another one here. This is the EEPROM. This is obviously containing the program for the device. And there's another one here. So we can have a look at the chips, see what they are. We can see what these two are. Yeah, these are obviously connected into these. There's no mention. This says 24 volts and 0 volts. So we've got an idea what that does. I'll clean these all up a bit. And then let's have a look at the chips we've got on here and see if we can figure out what it's sort of doing. The other thing I just noticed is these here are relays, 24 volt relays. Okay, so these are relays. And these are coming from over here somewhere and switching some sort of voltage. It might be these relays seem to connect where the power comes in. No, that's power in over there. Yeah. They're switching something, that's all I can say. They're obviously switching something. So there's lots of ifs and buts at the moment. This lot here are clearly opto isolators. These look like opto isolators from these connectors. So this is some sort of probably input, but it could be output. Switching something off. I mean, I don't know where these connectors go to. I don't have the machine. I haven't seen the machine. I've not been out to it. I'm hoping that the problem with this is going to be one of the voltage regulators, because it sounds like a supply rail is down. That sounds like what's wrong with it. I'll clean up the various things, at least so we can sort of see what we've got. Let's see if we can just figure out a little bit more what we have here. Let's start with the brains of this thing then. So it's a programmable IC, PIC. This is a microcontroller, PIC 16C65A. Probably not much we can do with that to test it, but we can probably see if it's working. Does it have a clock? Does it have power? Is it not reset? I'm sure we can get a pin out for that. Give us some idea, maybe if it's working, if we need to go that far. So this chip, TDA 1905, see what that is. I'll just make a note of these. 1905, because I'm not familiar with a lot of these. We have another one in the same area here somewhere. So we have two of those 1905s, yeah, two of them down there. These I'm certain are opto isolators without even looking them up. I can just tell they're opto isolators. Up towards the processor then, this is all upside down, so let's go the other way. We have these things. So 74HC573, 573. I think there's a shift register or something like that. 74HC573s. I think that's basically doing what I kind of described. I thought it would be doing. We have another one across here somewhere, up a bit. I'll find it. That one. Yeah, another one. So we have a load of these, whatever they are, shift registers or something. Then over the other side we have some of these. Not really sure exactly what they are, but a strange number. PBL. Yeah, I don't know this one. Or even if that's the actual number, PBL 3717A. This is the one where we have two of the same, and one's been bridged to the other one, basically some sort of modification. So that's what we have on there. This clearly is an EEPROM, so we don't need to look at it. What's this little thing down here? SGS Thompson again, ST. Oh, another one, 74HC08. This is an inverter or something like that, or some sort of gate. Okay, 74HC08. So that's all the chips on there. We can have a quick look for the data sheet. So let's just see if we can figure out exactly what these things are doing. TDA 1905. What are these things? I mean, I have no idea what this chip is. Oh, audio amplifier with muting. Okay, so we know these are the audio amplifiers, yeah? That's the audio amplifiers. What else do we have? 74HC573. Some sort of shift register, I think. Let's have a look. 74HC573. Or some sort of latch, maybe, yeah? Something like that. Okay. Aha, look. Octal D-type transparent latch. So this latch is in data from the switches, I would say, or from some other sort of settings, and the processor can read it in serial format. That's what I expect these are doing. So there's 8 of them in each package, octal latch. Yeah, that's what they are. A latch, basically, you can either write to it or read from it, I would think. Okay, that's that one. PBL, this is a strange one. What are these things? PBL 3717. Okay. Oh, well, we have a data sheet. Oh, our stepper motor driver. Okay, so these are some sort of motor drivers, and this is where this thing has been like modified or cobbled or something. 10 volt to 46 motor supply voltage, so this is probably what the 24 volts does. We have a pin out for it, so if we need to have a look around them, we can have a look without the information. And the last one, 74HC08, which I think was inverters, octal 8 inverters in there, something like that. Let's have a look. Or 6 of them, 74HC08. Oh, 2 input AND gates. So, AND gates, you have 2 inputs, 1 output. If both the inputs are high, the output is high. Yeah. Anything else, the output is low. So that's what these are. This is called a function table or truth table. You see, output is only high if both the inputs are high. And high means a voltage on it. Probably 5 volts, these chips. Yeah, typical supply voltage 5 volts, which we should have known really, because we have like two 5 volts and a 12 volt regulator on here. Okay, so that's basically what we've got. What you should keep in mind when you have something like this to repair is that these things basically are all the same, regardless of whether it's a PCB from an air hockey machine or whether it's a PCB from a coffee maker, yeah, or anything like this. They're all basically the same. So what you have is you have power supplies. So this is a power supply. These regulators are all part of the power supply. And these large capacitors are part of that as well. Fuses, yeah, anything fuses, regulators, usually large capacitors. It could be something else, but usually they're part of a power supply, yeah. And certainly the regulators, transformers are. So that is power supply. Then you will always have the brains of the item, the microcontroller or a microprocessor with RAM, ROM. This has got an EEPROM. The memory could be built into it. Depends on how much space it needs to hold the program, and to some extent to the age of the thing. So more modern ones will probably have the EEPROM built in, but they will have the brains, yeah, and that's what we can see here. And then after that, it's just input and output. So these are clearly reading the switches, that's input. These opto isolators to these connectors are obviously either driving something or inputting from something. Yeah, this is all, if you like, the interfacing, yeah, between the microcontroller and the outside world. By outside world, I mean the machine, the device, okay, that it came from. And these are motor drivers. We know they're motor drivers, so we know motors connect here. And fair enough, this is an audio amplifier because we know what the chip is. But hopefully you can see straight away that this is not just a jumble of stuff on a PCB. It has a layout. It forms an... How can I put this? It forms a whole, but from individual sections, yeah. So we've broken this down just into sections, and we know basically what section is doing what. And again, relays. So this is part of the switching circuit. Again, it looks like these they're 24 volt relays, so they're going to be switching something, some sort of device. So now you have that in your mind, hopefully it's no longer a mysterious thing. You can see blocks of it, yeah. And once you can see blocks, you can see structure. And from structure, you can then start to figure out where the problems might be and which block, and then break it down further. Okay, so let's see if we can find any problems with this and if we can fix them. I'll try and power this up, I think. We can have a look on the regulators first. We know where the outputs and inputs are, so we can check for shorts. We know the fuse didn't blow again. We can hopefully assume that is actually okay. So let's check for shorts on the inputs, the outputs of the regulator. If we don't find any problems, then we can connect the mains to this. We know where the power comes in. We can connect it via the light bulb current limiter. If that doesn't come on bright, which we probably won't because there's no load on this, we might as well change this as well before we do that. Actually, we know that's bad anyway. And then let's see what we get. Once we power it up, we should have all the voltage rails present, and then we should be able to at least see if we've got signals on here. These are probably inputs, I'm guessing, but I can't say for certain. Yeah, and we can have a look around these motor drivers, and that might give us some idea, but hopefully we're going to find something wrong, and maybe it's that, I don't know. Let's check for shorts then, anything obvious. We know where ground is, and as good as a place as any, it's the middle pin on this regulator. Does that connect to the metal tab? It probably does. Very corroded, this thing actually. Yeah, it does go to the metal tab. These, I don't like these probes. I bought them and they bend far too easily. They came with a number of replacement tips, but I'm not keen on these. I thought they'd be very good, and they don't seem to be. Or maybe I'm abusing them here. Maybe it's me. Let's find a good ground. There's a big metal area here. That might be ground. If it is, it should go to here. Yeah. Okay, we've got a ground. Right, so input to this voltage regulator, not shorted. Output is not shorted. Same with this one. Input is not shorted. Output isn't shorted, and then there was a third one. Oh yeah, it's down under here. Get all put together so you can see the meter, but I'm sure we'll manage it. Input is not shorted. Output isn't shorted, so there's no shorts on there. Anything that's obvious. This fuse should be okay because it didn't blow again. I'm not sure if this is reference to ground, but we can have a look. Well, it reads a lot. I'll change this capacitor then, and then let's power it up. I've just switched on the desoldering vacuum tool if you're wondering what the noise is in the background, so I might need it. Depends how easily the holes in this come clean basically, yeah. How easily they come clean. So we can easily get the capacitor out, that's for sure. Should just make a note which way round it goes before we do it. So negative is towards this end, so negative towards this heatsink. Okay, get hold of it, lean it one way, other way, just rocking it backwards and forwards. It's coming. So that's out. So that's our bad capacitor. It's a 47 microfarad 25 volt. It's not a low ESR one, which doesn't surprise me because it's not a high speed switching circuit. We can get the desoldering tool, and this should just do this nicely. Yeah. Okay, well that one didn't. I think it's a little bit clogged up actually, guys. Yeah, it's just got blocked, that's all. Soon sort that out. Well, I say soon sort that out. Well, that is really blocked up. Very unusual to get that blocked. I mean, it's going right to the end practically. Yeah, you can see how far down it's going. If this thing clogs up, you best turn the temperature right up. And then see if you can unblock it. Well, let's have a go. Nope. Nope. Okay, I've set it to maximum 480. Now, so we just got a thing to clean. That is quite difficult. Sometimes I have to turn it on maximum and get the hot air gun and heat this end of it as well to clean it out. Just gives a bit of extra warmth in this area. I'm not sure you're supposed to do this, but it certainly seems to help it. Okay, let's have another go. Now that's really hard to do. Well, now I've bent it. That's the worst it's ever clogged up. Yeah. Okay, I've taken the thing off the back. You see it's pushed out this big plug of solder in there. Need to get that off there without doing it over this PCB, obviously. That's cleaned it. Obviously that won't do anything now, but okay guys, that's how to clean one of them things out. Yeah. Now we can set it back down to its normal temperature. Okay, you can see what that was. So that's this, basically this plug of solder on the end of it. Now it should work. Yeah, no problem at all. Well, I've just got the capacitor off. I think you can clearly see actually that the negative end is here. This will be ground. Yeah, we know this is ground. Yeah, that's ground. And then the positive end looks like it goes to here. There's a little jump. No, actually it doesn't. I thought that might come to this. No, it doesn't go to that regulator. You go to this one? No, that's probably this one. No, I'm not sure of that. I thought that would actually have gone through to there. Okay, so it's, whatever it is, it's not supplying this one. And so where's this one coming from? Onto the input pin. A bit awkward. Probably stand it back up. There we go. You get onto the input of that. Where does that go to? Well, it goes to here. That goes to some of these diodes. It's not going to that. No, it doesn't go into that. No, it goes to the diode here. Okay, well that's where that goes to. Yeah, it doesn't go quite where I thought it would. This is obviously on another diode, some other sort of voltage rail. The fuse that blew, I was just having another quick look at this. So I think you can see actually one end of the fuse is going up under here. I wondered if this goes to these chips, but it doesn't. I just tried from here around all these chips, it doesn't go there. But that fuse looks like it goes to these diodes under here. Yeah, these diodes, and these will probably be going to these smoothing capacitors. Yeah, and it might be the plus and minus supply really. I'm not totally sure. But there's two capacitors, and I think that's what provides power to these. So We need to figure out where the 7 amp actually goes to, and just get down on there. Go to these. Not from there, no. We probably need to get the pin out for these. Actually, we have a data sheet and we can figure out where. Ah, goes there, yeah. So it goes to that one. So these are the largest capacitors on the board. You would assume that this is where the most power is. We know these are motor drivers, and we know that 7 amp is part of that circuit. So it looks like the fuse blew because either something connected to here, which come from these, or something wrong with one of these possibly, yeah. So that's something else we can actually examine. I've replaced the capacitor. Now let's have a look at this area around the fuse. So we can just check the fuse. He did say it was okay, and it reads okay. You can see on the meter. Yeah. These diodes, and they are all diodes marked D1, well, yeah, D whatever. Just get a torch, we get a bit more light in here. Okay, so you can see them quite clearly now. So I'm sure you can see the middle two have the stripe at this end, and they're both those ends connected together, yeah. So that effectively is a positive output, and then the other two have the other end, the anodes towards here, and I reckon they're the negative outputs, and I reckon that both the outer two are actually connected together. And the reason being, because I'm sure this is a bridge rectifier. So yeah, 0. So we know they're connected together, and these are connected together. So this is a positive output, and these are a negative output. Okay, and that's why we've got two capacitors here. So effectively, the capacitors, we can check in a minute, 2 of the pins will be connected together, the positive one and the negative of the other, and that effectively be the ground, the center tap. So I'm fairly confident that these diodes are feeding these chips. These are the motor drivers, and this is effectively what's being driven from the fuse at the moment. So if we just go onto here, so that's the negative end of one of them, doesn't matter which one because they're both connected together. That'll go to here somewhere. There. Yeah, I think I had it. Okay. So that is a negative supply, yeah. And there's be the same on the other chip, which is here. That's a negative supply. And I'm guessing the positive supply is probably the one opposite it. And it actually reads like a short. No, that's 0. That reads like a short. Unless there's some... there might be some capacitors charge up. Just give it a little moment in case. No? Let's go to this one again. So sometimes you get large capacitors that will look like a short for a little instance. Sometimes a little while then charge up. So they don't. Okay, so that goes to there. Then we can go on the output of the positive end of the bridge rectifier, which is either of these two in the middle. So let's see if we can get down in here. Bit awkward to get down there, but I'm sure I will. You probably can't see. I'm sure. No, I'm floating around. It's so difficult to reach down there. Okay, I've got it. I know I've got it, so if we go to the other one. Yeah, connected together. So that goes to our chips as well. Does it go on the other side? No, it doesn't. So maybe I wasn't reading a short across this. Maybe the positive pin is somewhere else. Let's have a look if we can find a connection. Yeah, that goes to there. Okay, that one goes to there. And I'm sure it'll go the same on the other one. That third one down. Okay, so we know both those supply rails go to there. And they're not shorted. In fact, I can just go straight across the rail here. They're not shorted, okay. So we need to have a look at the data sheet for these chips and just figure out what we do have here. We can just have a quick look to see if it looks sensible, and then we can power this up, I think. But it's likely, because the fuse had blown, either one or both of these have blown, or whatever was connected from here has blown. So I'm pretty sure we're going to find there's two motors, one here and one here. Yeah? And there's possibly something blown there. In fact, was I getting the bleep? Yeah, that's just reading the resistance. 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 The other possibility is that it's not that these chips have blown, but whatever is attached to here is short, and that's what blew the fuse. But it doesn't really explain why the fuse didn't blow after they replaced it, unless something went short and then went open. Now, motors, the only thing I can think of that would have motors on an air hockey table are effectively the blowers for the air, like the air compressor. I can't think of anything else that would have motors involved with it. Although I've never looked at the inner workings of one, but I mean, surely like the puck just goes down the hole in the goal and just drops into a little chamber below. And everything else is human powered. Yeah. So I suspect the only motors I can think of are actually connecting to here through the motor controllers. Obviously, they blow the air. That's what this fuse does. It's a 7 amp fuse. Depending on the voltage rail, we'll measure it in a minute. We can kind of work out, the maximum wattage that could provide. But if this is like a plus or minus 24, that's quite a bit, yeah. 7 times 48 is rather a lot. Okay, let's have a look at the data sheets for these two chips and see if we can just figure out a little bit more. So PBL 3717A. This is the data sheet for the chip. So we can actually see it doesn't have a positive and negative supply at all. It has all the middle sets of pins on both sides connecting to ground, and then we have these VS, A and B and so on. To see what these actually do, if we find the typical application circuit, we can see 3 and 14 are the motor supply, okay, and then we have a couple of 5 volt supplies. Well, in fact, we have a 5 volt supply and a 5 volt reference actually. And then all these pins, 4, 5, 12, 13, are ground. These are the ones we looked at around the middle. So, if we look again at our chip, we can probably make a bit of sense of this. It is a bridge rectifier, but it's not a positive and negative supply. So, from the data sheet then, we can work this out now. So, we know all these middle pins are ground, and they connect together. Yeah, 4 pins on each chip. Then we know that the ground goes back to our bridge rectifier, and it's on the negative end of it, which is there. The positive end of the bridge rectifier, which is the middle ones, goes to the supply rails, which I think we're on 3 and 14 on both chips. Yeah, so that's our positive supply coming into the chips, and it's there. And we don't have a short from the positive rail to ground. So there's no short there, so that's nothing to do with the fuse blowing. Although we sort of know that because it doesn't blow now. This modification on the back here, if you look at it, what they've done, they've taken pin, I think it's 15, let me have a look. Yeah, pin 15 and pin 1. So what they've done is they've connected pin 15 and pin 1 from this chip. They've disconnected them from this one and connected it to the same place. So these points here are the sockets, and we can say 100% now what they've done is they've wired both of the motors to run on one chip, and that makes me think it's because the other chip was faulty, and rather than replacing the chip, they've cobbled it. Yeah, I think that's almost certainly what they've done here. So I would be inclined to order chips and replace one or both of these, especially if it doesn't work. We also need to check the resistance of the load here, because that is effectively the load on that voltage supply, which says it's going to be up to 36 volts, yeah? Okay, so we sort of know what's going on around there, and we've got some idea why the fuse might have blown. Let's now power this up and check all the other voltages, which are the 5, the 12, and the voltage supply here. And then we'll have a better idea of what the board's doing. to do this, I'll use this little thing I made up. So it's just a socket, basically IEC with a couple bits of wire on, and I can tag this onto circuit boards and then plug them in. There's no earth because I don't need it. I have an isolation transformer on my bench anyway, so it's much safer not to have an earth around, to be quite honest. The isolation transformer, I've mentioned it before. It basically means I can catch hold of either live or neutral and I won't feel a thing, but it doesn't help you if you catch hold of both at the same time. But it gives you a good degree of additional safety, so it's definitely worth having one. I'll make a video about those. We'll just trim this a little bit shorter so it can't touch the other one. That should do it. And then we can apply some power. Now, I've already figured out, well, we've all done that, we've all seen it, where the power comes in on this. But I'm still going to connect it via the light bulb current limiter. So that means that if I had made a mistake, for instance, and this was a short, I mean, we can measure it, we know it won't be, it'll actually be the primary resistance of the transformer, which will be some ohms actually. Well, I should have a reasonable resistance. Let's have a look. 50 ohms, yeah, that's about reasonable. So I'll still use the light bulb limiter anyway. It shouldn't come on at all, really, to be quite honest, because this is not connected to any loads. But let's do that, and then let's measure some voltages around the board. So we're going to have a look. First of all, we're going to straight away see what is the output from the 3 voltage regulators that are on here, and what is the voltage supply on these chips. Okay, make sure there's no bits of metal under here. Let's have a go. The light bulb's here, so that's in series with the main supply, so the mains is coming through the light bulb. So when we switch on, I'd expect that not to do anything. Okay, yeah, just lit dimly, so it's drawing a little bit of power. Something went click and a light came on here, so that suggests this board is actually powering up. I'll just zoom it out a little bit so we can see all the voltage regulators, then we'll take some measurements. Let's power on again. So we're now just on a direct main supply. All the LEDs have lit up, that's a good sign. What have we got on our voltage regulators? We could do with finding a ground point. I was pretty sure this was ground. Over here. Let's try and use it. So this is the 5 volt regulator. So coming into the regulator, it's not a volts range obviously. Coming into the 5 volt regulator, we have 13 volts, yeah, and what's coming out should be 5. Well, it isn't. This should be ground, 0.6. So there's something wrong here with this regulator. Oh no, it says it's there. It's just had a bad connection. It's not very stable, but there we go, with no load. Yeah, why not? Let's go on this one. So this is the 12 volts. So coming in, 13, out. Oh, I tell you, that's another 5 volt regulator. Yes, it is a 5 volt, my mistake. Okay, what's on this one? So this is the 12 volt regulator. In, 16, out. Let's go on to it. 11.87. So we have all those voltages. Let's have a look at these chips here. So we know now that the ones around the middle are ground, and then pin, it was 2 or 3, I think it was 3. That's a 23 volt supply on there. That's a 23 volt supply. Okay, so we know we have all the supplies. The fact you get a relay clicking when it turns on suggests to me that this thing is actually doing something, because these relays are no doubt controlled by the PIC chip here. I think really I'd have to say initially I can't find a problem with this. It's quite possible that this capacitor was the problem if it's connected around one of these voltage regulators, which I'm pretty sure it must be. Yeah. What I'll do with this then, I'll speak to the guy and see if I can go down with him to the machine that it's connected to and measure the resistance of the motors which connect to here. I mean, either A, I've fixed it, or B, I need to check this out, because if there's a very high load here, it's possible when the load's attached, it drags the voltages down everywhere on the board. Therefore, all the LEDs are dim, for example. So I'll get in touch with the guy and let's see if we can go down to the arcade and connect this board. And let's see what it does. Oh, I have a bit more information about this. So the guy who brought it in to me spoke to the guy who owns the machine, and he says that he's got another PCB from another machine and put that into this one and it works. So we can say from that then there's nothing wrong with the actual machine, like short circuit loads or anything, which means basically the only thing I can find wrong with this was this capacitor. All the voltage rails appear to be present, unless maybe we have a situation where something is failing under load, one of the regulators, but I've no way to really determine that without actually going out on site. What we have decided is this will go back to the amusement arcade. He's going to try it. If it doesn't work, then I'll go out to the site myself and I'll take some measurements under load. We have a working one as well, so hopefully from that we've got a good chance of fixing this. If you've got any thoughts on that, get into the comments below, let me know what you think. But for now, this one is done as much as I can, and I'll let you know in the comments whether it works when the guy tries it in the air hockey machine. Ciao for now, guys.